All right, so today's topic is Kc, the equilibrium constant. Can we make sure, please, that you use a capital K, because there is a little k constant in chemistry, and it's a different constant, it's a rate constant. We'll come to that later on. This is the big K constant, the equilibrium constant, and the little subscript C just stands for concentration. So K is the equilibrium constant. The equilibrium constant gives us an idea of where the equilibrium position is. It's maths, isn't it? So rather than just saying shift to the left or shift to the right, we're going to put numbers on it now. Going to actually have some value. Now, what I've put on the screen there is an appalling kind of definition, which I find is no use at all. But that is the formal definition of Kc. You will not have to reproduce that in the exam. You'll be grateful to know what you do need to be able to do is generate the expression for Kc based on a reaction. But that is its definition, so that's why up there. When A and B are reactants and X and Y are products, N, N, P and Q are the balancing numbers, or stoichiometry is the fancy word for balancing numbers, then Kc equals concentration of X to the power of P, concentration of Y to the power of Q, over the concentration of A to the power of N, times the concentration of B to the power of M. Yay! Lesson done. Yeah, we've all learned and understood that, so we can move on. Yeah, we need some practice. All right. Okay. Let's just simplify it a little bit. I'm just going to have A goes to B. So first of all, we notice that B is on the top. Okay. So products over reactants. Important, that one. Try and get that in on the first day so you don't get into some kind of habit, because we go from left to right, A to B, so there's a temptation of A over B, but it's B over A, products over reactants. The reason for that is if we have a lot of products, we'll have the big number on top. K will be a big number. Big number means the reaction's going successfully, we're getting lots of products. If there's more A than B, then B over A will be a small number. Small number means not much product. I think that's a bit more intuitive. K is 1,000, we're getting lots of products. K is 0.1, we're not getting much product. I think that kind of makes more sense intuitively. The second thing is these square brackets. So putting square brackets around something, and I do need them to be square brackets, please. No sloppy, curvy ones, thanks. Square brackets means the concentration of X. And we pronounce them concentration. So this is the first time you've hit this notation. So it just adds a little bit more to the to your thinking there. And lastly, the concentrations are raised to the powers of their balancing numbers. So if I had 2A goes to B, it would be concentration of B over concentration of A squared, raised to the power of 2. Okay, that's quite a lot to take in one go. We'll do some practice. But let's start with the old Haber process. Nitrogen, 3 hydrogens and 2 ammonias. Makes 2 ammonias. So Kc, and I realise at this point I'm talking about gases, and you might say to me, hang on, Mr. Harris, you can't have the concentration of a gas. And I would say, yes, you can. you can have a certain amount of moles of gas in a decimeter cubed container. So you can have the moles per decimeter cubed of gas. Still works. Okay. So products over reactants. So NH3 is on the top. N2 and H2 are on the bottom. Square brackets meaning concentration of. And then raised to the powers of the balancing numbers. So NH3 has got a 2 in front of it, so that's going to be squared. N2 doesn't have a number in front of it, so I don't need to do anything to the N2. H2 is 3 of those, so it'll be H2 cubed. Okay? Does that all make sense? Oh, it's my next slide. Who knew? Okay. Let's have a go at some others. So for each of those equations, reaction equations, could you write me a KC, please? So our next step is just, I'm going to go back to this table. We're going to have a think about the effect on Kc of the various things. Now, remember that, where are we? Surface area and adding a catalyst don't affect equilibrium position anyway, so they couldn't have any effect on Kc. Let's have a think about what happens when we increase the temperature, and let's go back to our old friend, which I literally just rubbed off the board, the Haber process. Minus 92. Just remind ourselves what happens when we increase the temperature to the equilibrium position of the Haber process. Could somebody give me an exam answer? Explain what happens to the equilibrium position when we increase the temperature of the Haber process. Somebody want to dig in there? Go for it.
The equilibrium will shift to the left as the reaction is exothermic, and an increase in temperature shifts in the endothermic direction.
Okay, so shifts the equilibrium position. It's good to state the rule, because then you get that all-important word endothermic appearing in your answer. So the examiner now knows you know the rule. You increase the temperature, the equilibrium position shifts. I've written the word shifts. It's a live show, thanks. Shifts in the endothermic direction. Why? Should be 3 words that appear in your head, but I need to write down the specific answer. What were the 3 words that should appear in your head? Whenever I ask why anything changes in an equilibrium? Balance isn't quite the right word. Le Chatelier's principle? You can't just say chemical sounding words. What's Le Chatelier's principle? To minimize the change. Right, minimizing the change. But you can't write minimize the change for every question based on Le Chatelier, because they want to know that you know what you're talking about. So what's the change and how are we minimizing it? We've increased the temperature. So the equilibrium shifts in the endothermic direction to
minimize the change.
No, can't just say that. You won't get the marks for that.
Minimise heat loss.
Heat loss, that's not quite right, is it? We've increased the temperature.
So heat
We've increased the temperature. What does Le Chatelier say the equilibrium will try and do?
Try and decrease the pressure.
Decrease the temperature. That will be fine. Decrease the temperature. Okay, that's your minimise, decrease, and the change is the temperature. So decrease the temperature would be fine. I'm just gonna just explain it a little bit more. It's to reduce the added energy. The experiment, the reaction is absorbing the energy to reduce the amount that we added by increasing the temperature. Okay, so we've increased the temperature. The equilibrium is therefore shifting in the endothermic direction, which is, in this example, okay. So our equilibrium is shifted to the left to minimize the change, reduce the added energy. So we're making more, less? Less. The equilibrium yield of ammonia is going to go down. Remember, we talked about optimizing the conditions for temperature. We've got to have a balance between rate and yield. Okay, so here's our Kc then, NH3 squared over N2H2 cubed. What's going to happen to the value of that number? It's going to decrease. Okay, it's going to decrease. So we have to look at the equilibrium in exactly the same way as we have to look at the equilibrium if you want to work out the result of increasing the temperature. The result of increasing the temperature shifts this equilibrium to the left, so it'll shift this Kc down. It'll go down. As the amount of ammonia goes down and the amount of nitrogen and hydrogen goes up, the value of Kc will decrease. If we had an endothermic reaction going forwards, if the delta H was positive, then it'd be the opposite way around. You can see how it's easy to get all this confused, so you have to stop and think for a bit. Okay. Deep breaths all around. What happens if I increase the concentration of a reactant? Go on, Jamie.
Well, the equilibrium will shift to the right, which means that Kc will increase.
Super logic there. I don't think any of us could flaw that. What about increasing the pressure?
If the
They sense a
product
trap.
has more moles, then Kc will increase.
So for this equilibrium,
It will decrease.
okay. So this is a really, really important point, and I really want to stress this. What is Kc? Equilibrium. Is the equilibrium
Constant.
constant? Okay. It's the equilibrium constant. It is constant at a given temperature, regardless of what Jamie's logic just, might have really appealed to you. His logic was sound. But the equilibrium constant is, surprise, constant at a given temperature. So it changes with temperature, but nothing else. Okay, changes with temperature, but nothing else. There are no other reasons to change Kc. Okay, which is why I put it in large, loud, red letters. I suggest you do something similar, because it's a really common exam question. Because they'll ask you, you'll have an equilibrium that you've never seen before, and then they'll ask you about the effect of pressure on the equilibrium position. You'll have worked it all out. That side's got fewer moles of gas, so it must shift in that direction. You've written your Le Chatelier answer talking about it shift to the right to decrease the added pressure. That's to minimize the change. And you're doing all of this, and then it'll say, what's the effect on Kc? And you just sort of fall straight into that trap. It's really easily done. Happens all the time for unsuspecting year 12s. Okay, so please just make lots of noise on your page. Kc is a constant at a given temperature. Okay. Hard one now. Yeah, just put a summary there. So the equilibrium constant is constant for a given reaction at a given temperature. So not that constant. As you know, it's hardly like the speed of light, but it is still constant at a given reaction for a given temperature. So Kc is unaffected by changes in concentration, pressure, presence of a catalyst, chopping your lumps of calcium carbonate up into small pieces, whatever it is. For an exothermic reaction, an increase in temperature shifts the equilibrium to the left, which will decrease Kc. And if we had an endothermic reaction, it would be the opposite way around, but nothing else affects Kc. We're not going to do that yet. Why do I not have units on this slide? Oh, I see it. That's for the end. Okay. Let's just finish. By having some fun with units. What are the units of Kc? Well, it depends on the definition of Kc. Those of you with weaker algebra skills will need to pay close attention here. I love what just happened. Okay, I'm going to stay with the ammonia one here. So Kc equals the concentration of ammonia squared. Concentration is measured in
Mol dm cubed.
mole per dm cubed, or mole dm cubed minus 3, and we are squaring that, and then that's all going over concentration of nitrogen, mole per dm cubed, times the concentration of hydrogen, mole per dm cubed, cubed. Yay. What are we going to do with that to try and make it a bit simpler? Go on, Timmy.
You can cancel out
Okay. What would you like to cancel?
the bottom mol per dm cubed will come to the square.
It won't cancel.
Yeah, because it's 2 over it, isn't it?
There's 2 on the top.
Yeah,
There's only 1 on the bottom.
Yeah, you take 1 on the bottom, so you have 1 left at the top.
Okay. Could we? You can do that. There's nothing wrong with what you said. Could we simplify the bottom first?
Yeah.
What happens to powers when we
Yeah, you go.
multiply?
You have to add it.
We have to add them. So if I just leave mole per dm cubed squared on the top for the moment, how many mole per dm cubes do we have on the bottom?
-1. It'll be mole
What's the
It'll be mole dm to the -1.
mole per dm cubed? What power would I put there? 4. Okay, good. Now let's cancel. So cancelling, well, we're dividing powers, so we take them away. So what would I have?
Mole dm cubed to -2.
Okay, so
Mole dm to
it's
-3.
1 over mole per dm cubed squared. So we cancel both on the top, that leaves 2 on the bottom, and that's, we'll just go over here, mole per dm cubed to the -2. Okay, let's get rid of the brackets now.
Mole dm to the -6.
I'm going to do them separately.
Times. Do you multiply powers?
We do.
-3, and so you get -1.
What?
You multiply -3 and -2, don't you?
Yes. -3 times -2 is
Yeah, -2. Minus 6.
Minus 3 times minus 2 is minus 6.
Oh, minus 3 times 6.
Oh, I haven't done the moles yet.
Mole dm 6.
I've got moles are a separate unit. It's moles,
Mole
dm minus 3. What's
mole
the...
per dm 6.
No. John?
Yeah, moles to minus 2 and then
I've got to have moles minus 2 dm 6. I'm just going to put a plus sign in there just to emphasize that. If you want, I often go from this point. So I would say 1 over moles squared dm minus 6, and then you can. So then you're only doing one thing at a time. You're multiplying out here, and then you're changing the signs there. We have a little bit of time. Just have a go at writing the units for, let's just say the first three of these. Just give me a unit, please, for those. We'll come back to one in a moment. Let's do the first one first. Oh, sorry, the second one first. Units for 2 would be, well, it will be mole per dm cubed over mole per dm cubed times mole per dm cubed. Cancel, cancel. No, 1 over mole per dm cubed. So that will be
Mole dm cubed.
no. Mole minus 1 dm to the 3, the plus 3. The second one,
Oh.
mole per dm cubed over 1, 2, 3 mole per dm cubed to the 3 is 1 over mole per dm cubed squared
So that means mole minus 1.
moles minus 2 dm
dm 6.
plus 6. Very good. Right, let's do the first one.
Just 1.
What's the units? One's
1 joules.
no, no,
Just 1.
no. What are the units?
mole 1 dm 1.
Oh, mole 0 dm 0. Oh, 0. See, now stop to the rest.
No, you.
It has none.
Full of tricks.
Full of tricks, yes. That's chemistry.